Today we're going to talk about how riflescopes work. It's important to understand exactly how they work so that we can know how to operate them properly. Today we're going to be showing an example of an Arken SH4 6-24 power riflescope. It has a 34 millimeter main tube, that's the diameter of the main tube, and a 50 millimeter objective lens. Not all riflescopes are going to possess all of these features, so if we talk about something that your scope does not have, just make a mental note of that and continue on with the lesson. So before we talk about how to mount a riflescope, set up the diopter parallax, how to bore sight it, really get everything squared away, it's important that we understand mechanically how these things function. There are a lot of different parts. This is delicate instrumentation, and there are a lot of features. If those features are not adjusted appropriately, the optic will not be performing as it is designed. A lot of times people think they have a bad optic, a bad scope, and they simply did not realize that something needed to be in focus, in parallax, adjusted appropriately. They did not realize the torque specs on the ring caps had to be a certain limit, or it would compress the tube. There are a number of things about optical sights that are highly intricate and delicate, and one must understand how they work in order to manage these appropriately. In order to really be able to manage your system, the optic is probably the most fragile component equipment-wise attached to your rifle. Okay, this is a very complex instrument. There's a lot of stuff in here. You want to kind of take care of this, handle it like a baby as best you can. There are scopes that are pretty darn tough, but even the toughest of scopes is still a fragile instrument. Okay, the light is going to enter through the front of the scope, obviously, of whatever you're looking at. Let's say you're looking at a pine tree down there, and the light enters in, and you have the objective lens is the first lens. Okay, that's going to cross that light. It's going to focus it and constrict it down here. Well, it's going to crisscross at some point, right in here. Okay, where this first focus point is, it's called your first focal plane. Okay, so light's entering through the objective lens, and your first focal point, the first place it focuses, is your first focal plane. And so once it gets in here, inside the scope, you have the outside tube here, which is 34 millimeters on this particular scope, okay? And on the inside, you have a smaller tube that's like a baby scope, okay? We're going to call that the erector assembly, okay? It's a small tube with a lens stack in it, which is actually indexed on the bottom by a spring. There's a pivot mechanism in here in the control group, and you have the elevation turret and the windage turret. These are basically large caps that tighten down on screws, and the screws are like any kind of machine screw. Where you tighten down, it actually pushes downward on the erector assembly inside of here, and that's what gives you your vertical adjustment. So when you screw this in, think about it like this. Pay attention, it's very, very important. When you screw this screw in on most conventional rifle optics, clockwise, you're pushing it down. So you're pushing your point of impacts down. When you unscrew it counterclockwise, you're pulling your point of impacts up. Important to memorize that stuff for the dark when you're trying to dial stuff when you can't see your numbers, and you can just count your clicks. Likewise, left and right. If you screw it in, okay, it's a machine screw, pressing on that little baby scope, the erector tube inside there, okay, baby scope, I made that up, okay, it's not a real term. But this is going to screw in. Your traverse adjustment here is a machine screw is pushing your impacts left. When you unscrew it, you're pulling it right, okay? So you don't need to look at the L and the R or which way is up and down on your scopes if you kind of think about it like that. And it's nice to be able to speed up your corrections tremendously if you don't have to think about which way to turn. So when you're dialing, try to do it without looking and see if you can get it right. Basically, you unscrew it counterclockwise, pull it up, screw it in, push it down, okay? And so once this light, so you have an upside down image after it comes through the first focus point called the first focal plane. This erector group, that baby scope in there that's being pushed on by the control group, which is this series of screws, basically, and on the other side corner, if you look on the bottom corner there is a spring, a counter spring, which pushes up. Some of your German optics have what they call the Wetzlar 5-piece mechanism, where there's actually little arms that will index more evenly on these different components on the erector tube, so it's not pushing on like the side of a circle, and that's why they're very, very precise optics. But most of your conventional designs, anything made in Asia or the United States, is a three-piece design. Effectively, a screw here, and a counter spring on the back side. The Germans added kind of a camming lever arm here and here on the Wetzlar 5-piece. That's just a side note. But basically, you have your upside-down image here. It needs to be re-erected back upright. And so when it comes through the erector tube, the job of the erector tube is to re-erect the image back upright. So the image will flip back upright, so that when you're looking at it, you're not looking at upside-down land, okay? After that image has been re-erected, you are now in what they call the second focal plane, back here. This is the second focal plane. And then hopefully you get your eye placed properly behind the scope so you see 360 degrees of crisp, perfect circle on the back here. And you can dial up and down, and you're good to go. How to base, that's how a scope works. That's why reticles that are placed in the first focal plane, what basically effectively happens is when your image of your pine tree or your deer or whatever you're looking at, bad guy, right, is coming in through the front, that image is married to the image of the reticle, which is placed in the first focal plane. So now your reticle and your image are superimposed into the same light, okay? So it's that image is all one piece, okay? So one piece image. When it comes back, it gets re-erected, you zoom in that entire image of the reticle superimposed on whatever object you're looking at. That's why you can zoom in on the first focal plane, and your subtensions remain proportional to the image that you're looking at, because you're zooming in on all the light at once. When you place a reticle in the second focal plane back here, basically you're zooming in on the image, and then the reticle is behind that. So your reticle will actually stay the same in the scope, but your image will be getting larger and smaller when you magnify and demagnify, okay? So when you turn it up or down. And so that's why it's that way. There's different preferences. Second focal plane, you know, there's advantages. It stays sharper. It stays fine aiming points. A lot of guys like that. A lot of target shooters or extreme long range guys prefer that for that application. If you're dialing a lot and using your mills a lot and you're getting in their more chaotic environment, a lot of guys like to have it in the first focal plane. This is purely user's preference, okay? Whichever works best, okay? So that's how the first focal plane scopes and second focal plane scopes work, is where the reticle is placed within there. So after the image is re-erected, it's going to exit out the back of the ocular, and it will have a certain diameter to it, what they call an exit pupil diameter. It'll be a larger diameter if it's on a lower magnification, and it'll be smaller if it's on higher. That means that when you're looking behind the scope, that when you're sitting behind the scope looking through it with your eye box is going to be tighter, the area in which you can see clearly through the scope. When it's at higher magnifications, it's going to be a lot more fussy with exactly where your head is placed behind it. Likewise, if it's a lower power, you have a larger exit pupil diameter. You have a little bit more wiggle room in there to where you can still see nice and crisp around the scope. One thing to keep in mind is parallax. Parallax is basically a displacement or a difference in the apparent position of an object viewed along two different lines of sight and measured by the angle or the semi-angle of inclination between those two lines. So when you shift your position, the parallax is going to make it appear as if you're still on sight, and it might not be. So a parallax knob is actually going to bring both of your focal planes, your front focal plane and your rear focal plane, into alignment in such a way to where your head moving behind the optic slightly is not going to exacerbate that displacement in the position of the target in relation to the reticle on the target. All in all, the parallax is simply the alignment of the focal planes along with the reticle and the target and your eyeball. If that is off, what's going to happen is your reticle will appear to be on the target, but in reality, you're out of alignment. There was a parallax displacement that made it appear to be there, but it wasn't, because there is a certain cone you can get away with to where it appears to be right. The parallax adjustment is going to take the slack out of that, so that even if your head moves slightly, the reticles are going to stay fixed on the target in such a way to where your parallax is minimized. And that's going to reduce the amount of error that takes place when you're aiming at your target. A very, very, very common thing that occurs, and I've seen guys change barrels, change loads, try new powders, try new primers. They thought their scope was loose or broke. They rebetted their stock. They spent thousands of dollars and decades chasing zeros, chasing loads, and chasing new equipment when they didn't realize how important parallax elimination is in the optic. If you do not have your parallax minimized through the adjustment of your parallax knob, that displacement optically is exacerbated, and you think you're on sight, but you're actually a few inches off. That'll result in shots being thrown right, left, up, down. Instead of shooting 5 shots in one hole on a precision rifle, if your parallax is out of whack and your head is moving around just a tiny bit behind the scope, it will exacerbate that problem, and that rifle might not even be shooting to where it could be. It's very important to understand what parallax is and have that eliminated in your optics so that it works to the best of its ability. In order for the parallax to function properly, there are components within the scope tube that need to slightly move forward and backwards. If the scope tube is deformed in any way, that will inhibit the operation of the parallax adjustment. Likewise with the magnification ring. Basically, you turn the magnification ring and there's a series of lenses that move slightly forward and backwards to zoom in on the image. And if the scope is deformed, your magnification will not operate properly. On cheaper scopes, you might have a slightly different point of impact based on what power setting you are adjusted to, because those components can be tight or loose depending on the quality of the optic. Higher quality scopes typically are going to have less effect when you zoom in and out. It should hit in the same spot, but do be aware of that. The ocular adjustment is another part of the scope in the very, very rear. We'll talk about that when we actually show you how to set your reticle up before we zero our scope. But again, we have components that are screwing in and out of a tube. That tube cannot be deformed. Now, in terms of the mechanical adjustment range of the scope, when you're zeroing the scope, you have an elevation turret that's up and down. You have a windage turret or a traverse adjustment, which is left and right. Those are screws, machine screws that press on that erector group. You have a counter spring on the back. Here in the picture, it's a coil spring. It's actually usually a flat spring. I just put that in there so you guys could recognize it as a spring. The precision machining of the threads on those screws is going to determine how precisely the tracking graduation precision is on that erector group, that control group. You want that to move with precision, exactly that angular unit of adjustment, so that you can make a hit on your follow-up shot. There are a variety of different scopes, typically your budget scopes or some of your hunting scopes, and a lot of your red dot sights, prismatic sights are going to have smaller adjustment screws. They're not going to concentrate on the quality of those precision machine screw adjustments for the control group. They will just move you up and down, left and right. It might be pretty close, but it's not going to be exactly on. On a target scope or a tactical style scope with externally adjustable target turrets, they're going to try a lot harder to make sure those machine screws are going to adjust appropriately. Now, one thing you have to realize about the design of the scope is that the part that you see, the knobs on the outside, are simply very, very thin aluminum or steel caps that are tightened onto an inner screw post, which is the actual mechanical part of the adjustment. The outer cap is what has the numbers on it and is what you use so you can actually index the adjustments. The inner screw is actually the part on the inside that mechanically adjusts the erector group. Rifle scopes are typically adjusted in angular units of measurement, either based on degrees of arc or radians of arc. Most of you understand that there are 360 degrees in a circle. For every 1 degree of arc, which is a very, very small angle, you can chop that degree of arc into 60 minutes. So 1/60th of a degree is a minute of angle. Typically, rifle scopes will have a fraction of a minute of angle to be a click value. So every time it clicks, that is a certain percentage or a certain fraction of a minute of angle. Most scopes are 1/4 click values. That means you have to go 4 clicks to make a full minute of angle. A very common unit of measurement used in modern rifle scopes, especially in the tactical world, are milliradian adjustments. A milliradian is simply 1,000th of a radian. A radian being that same distance from the radius of a circle to the outer edge, to the circumference. If you take that radius distance and wrap it around the edge of a circle, that is a radian. You chop a radian into 1,000 parts and you have a milliradian. Now, for most milliradian based scopes, 1 click is going to correspond to 1/10 of a milliradian, hence the 0.1 mrads per click noted on most of your turret caps. That means you have to click 10 times to get 1 full mil or milliradian. In terms of how much these click values adjust the optic, 1/4 minute of angle clicks cover slightly less ground at any given distance, as do 1/10 mrad clicks. For example, if you are at 1,000 yards, one click, a quarter minute of angle click on a minute of angle adjustable scope is going to correspond to approximately 2.5 inches at 1,000 yards. A milliradian click, if you have one click that's 1/10 of a milliradian, that's going to correspond to closer to 3.5 inches approximately. 2.5 inches for the quarter minute click, and you have 3.5 inches for the 10th IMRAD click. They're basically both very close to each other. Nobody that I know can hold that small. It's approximately 1 inch of difference between the two different click units at 1,000 yards. If you can find anyone that can consistently hold to within 1 inch at 1,000 yards, give me a call. I'd like to talk to that gentleman and buy him a Daniel Webster cigar. Because of the practical compatibility between both systems, they are effectually both synonymous in terms of angular adjustments, and thus I would highly suggest that your selection criteria for units of measurement, whether you want a minute of angle scope or a millrad scope, should be based on what you understand. Guys that have been running minute of angle scopes for years will understand those a lot better. At 100 yards, it's approximately 1 inch. At 500 yards, 1 minute of angle is going to cover 5 inches. At 1,000 yards, it'll cover approximately 10 or 11 inches, etc. Whereas MRADs is simply a different measuring stick. A 1 meter target's going to cover 1 mil at 1,000 meters, or 2 mils at 500 meters, etc. So they're both angular units of measurement. It's just simply a difference between whether you're measuring that angle in degrees or radians. So use whatever makes sense. Also take into account what the other guys you're working with will be using so that you're speaking the same language. That's a highly important point as well. The way you would test the precision tracking of an optic like this in terms of determining what the tracking graduation precision level is to set up what I call a truth stick test, where you get a known distance at 25 meters, where you simply use trigonometry. You aim at a measuring stick at a certain distance, you do the trigonometry, you dial the scope a certain amount of angular units, and you verify that it actually traversed that proper amount of space at that distance to match the units of adjustment that that scope is supposed to relate to. If it's off, I can measure by how much and simply do a percentage calculation of percent error of the tracking, and I will be able to get a pretty good idea of how that scope is performing. Likewise, you can also measure the reticle using a true stick. It's actually pretty easy. It's very important to get the exact distance right. If you're at 25 meters and you find yourself to be about 9 inches off, that will correspond to a significant error. You're going to be about 1% off at that distance. You are going to want to make sure you survey that distance and get an exact measurement. A laser rangefinder might not cut it. You might have to get surveying equipment out there or a measuring tape properly tensioned in a straight line to determine the exact distance. And you're going to measure from the control group to the stick. Keeping in mind you don't want any radical angles. You want to get it perpendicular to the stick. Make sure the rifle does not move. Make sure the optic is not moving at all. Dial your distance, dial it back down. Confirm that the optic did not actually move. Repeat the test several times to ensure you got a high degree of precision, and you will have your percentage error for your tracking graduation precision. Now that we have a better idea of how rifle scopes work, in the next video, we're going to talk about how to properly mount a rifle scope. Just before the 10 mil mark, and 34.5 is just past it. Let me reconfirm. Yeah, it's maybe on the far edge, about 0.5%. Okay, so now we're going to index all the way up to 68.75. minutes of angle, which will be pretty much right on the money with 20 full mils. So we already got up 30 something. We're at 40, 50, 60. We need to come up to 8. 68.123. Okay. All right, it's off about very close, about 0.5 centimeter far. Okay, so we'll come back to 0. Confirm we didn't touch anything goofy. It all wiped out. Yeah, we're right at the top of the stick. So it's a tiny bit far. It's less than 1% off. It's probably about, just going off top of my head, around 0.5 to 1%. overshooting the mils. So that's actually pretty close. That's well within industry standard. That's going to be better than most of your Japanese optics. This is not a Japanese optic, but it's well within that. It's underneath 1% error, which is actually very, very, very good.